Okay. Hello, everyone. Have you ever seen a discipline that entices so much creativity and excitement? I mean, come on. No field is so enthusiastic to their field as this one. And it's absolutely miraculous. And hence all this stuff that people are making, or classes people are teaching. I mean, obviously, there's a lot to say about it. That's a good one. That's a good find. Just pretty recent from October, I think it was released. So keep going, keep going. How's everybody doing? Thank you all for all of you showing your faces. I appreciate that. Very kind of you. Makes it so much nicer to teach a class, to be able to also see some feedback from the people actually listening to you.
Hey,
And
Mickey,
again, I appreciate also. Yeah,
can I say something?
you
I
could
got
always
a
say something.
vaccine!
No!
Yeah,
Oh, congratulations.
Woohoo!
I didn't realize you're 65.
I'm not. And I got one anyway, but I'm close.
Congratulations.
Thank you. Yeah, it's on campus.
Stay
It's for
safe.
real, you guys.
Oh, you got it on campus? Oh, wow. Just like an email or like they sent you or like
I
what
got
would
an
you do?
email. I got an email yesterday, and I got the vaccine an hour ago.
Oh, wow.
So they're
I
working
heard some
down.
other old people getting, yeah, I heard some other old people getting, um, getting emails from Tang
Yeah,
Center.
yeah.
Oh, it's gonna be a while for me. I don't know. I mean,
You're
like
right behind me, baby.
always behind you, Anita. Always behind. All right. So are we ready? We're going to continue. We had a nice, you know what we did last time? Remember? You know what really MRI is all about? Woo! Woo! It's all about rotations. MRI is just all about rotations. Rotations, 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 rotation. That's what really MRI is all about. It's just rotations. And turns out rotations also create some frequency and this is it's good stuff. So we're gonna talk more about rotations today, right? So let me any announcement, Ekin, apart from this really good news from Anita?
No, I can't match that news, so no.
All right. Okay, so let's see. I think we landed somewhere around describing precession, right? I think that was the beauty. All right. So we're continuing chapter 4 of the book. Um, and this is the physical description of MRI and then also mathematical description. And last time we derived pretty much the precession. So when you have a magnetic moment and you have also a spin angular momentum, when you put that spin in a strong magnetic field, the dynamic can be described by the following linear dynamic system, which is described by this cross product. So minus gamma B, this is the field, gamma geometric ratio, this is the magnetization vector. So it's a gamma B cross M. So the change in the magnetization with respect to time is given by this cross product. And whenever you have something that changes in time that is a function of a cross product, that always leads to some rotation. Okay, whenever you have this cross product, you get rotation because effectively, if you look at the eigenvalues of this matrix over here of this matrix, you'll see that it will have eigenvalues equal 1 And so those correspond to just rotations. Now, that can be either described this way or described this way. So the minus or plus, whether you want to pick your own poison. But one of the issues that we saw is that if we so effectively we've got this linear dynamic system, but it's really hard to see what is really the dynamic, because if I look at what the B field is, I can say that, for a good approximation, B equals B0 in the K direction. Because all the other components, the gradient fields, the RF fields, they all are very, very small compared to B0. So the main dynamic is driven by these by the main field, and that causes precession about the Z direction, or about K hat. But this is really a strong. This is the strongest type of dynamics. But it's very hard to see the subtle stuff that actually has a huge impact after some time. So it takes some time to have an impact, but it does. And so in order to be able to see it, we need to somehow remove the effect of B0 to model this system without the effect of B0, such that we'll be able to see the effect of the B1 field and the B2 fields. Not B2, right? We said that there's
The gradient?
gradient field. Thank you. The gradient field. And so in order to do this, what we're doing is a change of coordinate. We move from the lab frame into a rotating frame, and it's a rotating frame that rotates at the Larmor frequency omega 0. And then we showed last time that in the rotating frame, depending on what frequency you rotate, you can actually describe the B field in this particular case. And then what happens when we're looking at a rotating field that is actually rotating at gamma B0, then the main field goes away, because remember, all the dynamic that the main field causes is just rotation around K0. So once we rotate at that velocity, at that angular velocity around K0, then we effectively remove the effect of that field. Hence, in the rotating frame, the only components that are left are the magnetic, are the gradients. So G dot X that is pointing in the KR direction, so still pointing up. And then the B1 field, which is in the transverse direction, right? And we have two components, one in X and one in I. And this is much simpler description of this dynamic. And effectively, the magnetization then will precess about the applied field. So it will be precessing around either the gradient field or around the B1 field, or if you apply both, then it will precess about their superposition. So if we apply in the if we apply a B1 field, let's say in the I direction in the rotating frame, then our magnetization will effectively precess about this axis. Okay, precess about the applied field. So precess around the I axis, which is also the X axis, right? And then at what velocity? Well, that depends on how strong that field is. So it will precess at a rate which is gamma the magnitude of B1. If we apply a stronger B1, this will precess faster. If we apply a weaker B1, those precess slower. If we apply the B1 over here in this direction, then the magnetization will precess around this direction. Now, because the B1 field is always in the transverse plane, hence precession around the B1 field will always tip the magnetization from pointing up to somewhere that will have actually a transverse component, right? If there is no B1 field, let's say we remove this for a second. Okay, let's say we remove this, and we only apply a field in this direction, like in the direction of B0, well, then we have a degenerate precession, like nothing would happen pretty much. The magnetization kind of precesses around itself, around its own axis, but it's pretty much a degenerate precession. The fact that we are applying now a field that is perpendicular, then that causes the magnetization to tip, and this is really the dynamic that it's going to be producing. Okay. Now, this is all due to effectively describing the dynamic linear system as a cross product that leads to a solution, which is rotation. Rotation at a frequency, which is gamma v1. Now, I can also write that, the solution, as the magnetization as a function of time equals Rx as a function of omega t, where Rx is some rotation. It's a rotation matrix with an axis of in the direction of j or the direction of x, multiplied by the initial condition of where the magnetization is. So if the magnetization is pointing here, then applying a rotation matrix about the x-axis will then rotate it slowly around this direction, where Rx is effectively this following matrix. Now you can look at the book, equation 2.29. That's in the book. It's in the chapter 2. You can actually go and see. So this is rotation around the x-axis or the y-axis. Now, what happens when we apply a gradient? When we apply a gradient, well, in what direction does the gradient field pointing at?
The z direction.
Yeah, you're not asking a question because I know that all of you that did this are actually pointing up, which is really pointing in the direction of the main field, or the k direction or the z direction, right? So if our magnetization somehow gets into the transverse plane, and how does it get to the transverse plane? Well, if we do something like this, it can get actually to the transverse plane. Then if we apply a gradient field, then the magnetization will precess around the gradient field. How fast it will precess? Well, that depends. It depends because it's pretty much gamma times the magnitude of g dot x, the dot product between the gradient that we're applying and our position. Where we are in space. So it will pretty much precess along this direction. So this would be dynamic. But if we are, what would happen if we're exactly at the center of the magnet? What would g dot x be? Yeah, it will be 0 because at the center of the magnet, the gradient field is 0. Like we're not, I mean, a gradient field pretty much is a linearly changing field as a function of space. So at 0, it will be 0. So g times x, g dot x, where x equals 0 will be 0. So there will be no precession happening. And the magnetization will just stay here at the middle of the scanner. Well, as we move towards the x direction, well, then g dot x increases. And so the precession is going to increase more and more and more. Okay, so let's say we apply this gradient field for, let's say, 1 millisecond. So after 1 millisecond, magnetization that was at the center of the magnet will stay over here. Magnetization that was, let's say, on the right will evolve, right? For this, how much did I say? 1 millisecond. Let's say will evolve over 1 millisecond. And we'll end up pointing at this direction after, let's say, 1 millisecond. If we move further in x, then magnetization that's a little bit further to the right would precess even more and will end up actually being, let's say, over here. And what about magnetization that is on the left side of the magnet?
Going the other way.
In that case, yeah, x is negative, so g dot x is negative, hence the accumulation of angle or the rotation angle will be the other way, so it would precess the other way and would end up being over here. So you can kind of see how applying a gradient creates a spread of angles of spins throughout the volume. Okay, so this is what it does. Now, what is the actual dynamic? Well, the actual solution is actually m of t equals rz. So it's a rotation matrix about the z-axis. that rotates at omega times t times m0, right? So m0, so what's initial condition we have? And what is the rotation matrix around z? Well, it can be described using this matrix. And again, this is equation 2.27 in the book. Okay, so if I tell you now, I'm applying a gradient field in this direction for a certain amount of time, well, if you know the position of the spin and you know what is the size of the gradient and how much time it is applied, you can apply this rotation matrix to the initial condition and you know where it's going to end up with. Okay, that will be the solution. If I have, let's say, magnetization in this orientation, and I apply a B1 field in this direction, well, then the solution will be applying a rotation matrix of omega times t. Well, it depends what is omega for this case. Well, it depends on pretty much gamma B1. So rotation matrix multiplied by that initial condition, you can figure out what is the flip angle, or how much this magnetization has been flipped using this RF pulse. In the similar way, if I would have applied, instead of applying in this direction, let's say I apply the RF field in this direction, well, what would be then the solution? What will be the solution in this case? Well, in this case, m of t will be equal to ry of omega t multiplied by m0. Okay, because now we're applying it in the y direction or the j direction. So the rotation axis will be around this magnetization. And so after a while, this magnetization will tip and end up actually being over here. Okay, if we do a 90-degree rotation. Does that make sense? Any questions?
I have a
So
question.
rotations, yeah.
From the homework, we had a gradient that was nonlinear, and I was wondering why that, like, if that's something that we're trying to make happen, or was that just something because, you know, real life is never the way we want it to be, and how we handle that?
Yeah, it's pretty much real life is the way it is, and actually the way we handle it is we apply corrections afterwards. I mean, if x is not a if the field from the gradient is not g dot x, but it's some actually nonlinear function of x, then that's going to have some consequence when we try to figure out what is the position where that spin is. Because if we encode position by looking at the frequency, which is g dot x, and we solve for the position according to that, if it isn't, then it's going to be mapped to a different position. And what you've seen in the homework, that effectively spins that were at some position will be mapped to another position because of that. Okay, so you'll have what's called the geometric distortion. But if you know the mapping, you can correct for it. You can correct for this geometric distortion.
But we're never trying to actually get a nonlinear gradient, I'm assuming. Like, nobody, that's not, I wouldn't think it would be a great way of going about it, but maybe.
Well, okay, you know, like everything in MR,
It depends.
Depends.
it depends.
Or
That's
spins,
right.
something like that.
Because actually, sometimes you want to make the field very homogeneous. And when you put a sample, we said it, when you put a sample, let's say a head inside the magnet, it actually distorts the field. And so it's very hard to correct for that field just using linear terms. So to make that field uniform, I mean, it's pretty much the distortion is nonlinear throughout space. And so if we actually want to make the field more uniform, people have added what it's called shim gradients. So are gradients that you can pulse, but you usually don't use for imaging. What you use them for is to try to make the field more homogeneous. And they usually have nonlinear terms like x squared, z squared, xz, yx, and all sorts of terms, such that when you try to make the field uniform, you can apply these fields, and then they will try to what's called shim the field better. Does that make sense? But usually they're not used for imaging. However, saying that, there's actually a growing field of leveraging actually non-uniform gradient fields in order to do imaging. And if you want to look at some of that literature, it's called O-space or Patlock type of gradients. And there are some advantages of disadvantages of using those. And that could be actually a fantastic project if you're interested, either simulating or doing some literature search, or maybe building a nonlinear gradient and then like using it in the scanner. We have the hardware to be able to do that. So it is possible.
That's awesome. I'll definitely take a look. Thanks.
Okay, yeah, sure. Okay, so what happens when you apply both fields together? So let's say we apply B and we apply also G dot X. Well, then the contribution of that would go into this direction. This would be the total field. And then the solution will be then a rotation about this axis, about the total magnetic magnetization vector. So in that case, M of T will be equal to RZ prime, which is some arbitrary axis, with some degree alpha multiplied by M0. Okay, so it'll be rotation about this arbitrary axis. And if you want to look at how to actually, what is this rotation matrix, look at equation 2.35 in the book. You'll have some homework where we're going to apply some, like an RF pulse and another RF pulse and then a gradient. And then we'll ask you to do some analysis. And all this analysis would be done then by applying these rotation matrices to some initial condition, right? That will be pretty much, you won't need to solve directly like differential equations for that, because we know that the solution when you apply those fields are just simple rotations. Okay, so you'll see that in some of the homework. And the rotation, again, the angular frequency is gamma. In that case, will be B1 plus G dot X, the magnitude of that. And so it will be something like that in this case. All right. So now we know kind of what is the dynamic when we apply a gradient or an RF field to a magnetization. And you can kind of think of it like we can actually manipulate the magnetization to pretty much be almost anywhere that we want, right? Like if there is one spin somewhere in X and Y, like somewhere in space, one spin, we can move that one spin to pretty much anywhere we'd like to, right? Just by applying a RF field and some gradient field. So we could do that. The problem is if we want to now control an ensemble of a spin and bring all of them to a particular state, that could be complicated, because a gradient field, when you apply it, doesn't affect a single spin. It actually affects all the spins in the volume, and depending on their position, it would rotate them at different fields. Whereas the RF field, if you remember, applies the same thing to the entire volume. Does that make sense? So using a combination of RF fields and gradient fields, it is possible to arbitrarily move the magnetization to maybe a desired position. And for example, with slice selective excitation, this is exactly what we'd like to do. We'd like to knock down spins with a particular position, and we don't want to touch spins that are not in that position, like anywhere else, right? That's kind of like the idea. And there we're going to apply an RF field as well as a gradient field, and maybe we'll kind of change them somehow such that we get what we want. Okay, and we'll talk about that. In fact, one of the ways that people have used to design radio frequency pulses was using optimal control techniques, because this is really a control problem in some way, right? Like this is just a linear dynamic system that you can change, and then that would manipulate your magnetization. But there's other simpler way to derive it, and we'll see those as well. Okay, so the next type of, so this was rotations, right? That's when there's no losses. Remember all these, the B1 field, the gradient field, the B0 field, they all perform, have a dynamic which is just rotation. Rotation preserves length. So there's no loss and there's no gains over there. It's just perfect preservation of the length of the magnetization, but you just move it around. However, in MRI, there are also mechanism for loss, so loss of signal, so mechanism for relaxation, and also gain that comes in from recovery, and we're going to talk about those now. So the first one is T2 decay. If you remember T2 decay, in the toilet analogy, it would be what is the effect of the on the transverse magnetization? How the transverse magnetization, if you have some transverse magnetization, that once you have this transverse magnetization, that immediately starts decaying somehow. Now, why is that? Well, this is because of loss of coherence between spins. It's also called a spin-spin relaxation. So when somebody says T2 decay or transverse relaxation, they also refer to spin-spin relaxation. And the reason is because when you have a spin has a field, which is a dipole field. And if I put another spin next to it, well, the field that this one generates also affects this spin, and the field that this spins generate also affects this one, but also affects this one and this one and this one. And it becomes a very complex problem. But you can actually model this complex problem by effectively seeing that, oh, there's going to be, this one sees a slightly different field because of the effect of this one, and this one will see a slightly different field because of the effect of this one and this one and this one, and so on and so forth. So after a while, if you actually look at the precession frequency, this will exhibit slightly different precession frequency as this one, and this one will exhibit a slightly different frequency than this one. And eventually, the magnetization vectors of all of these will kind of have a spread, which will lead to some destructive interference of the signal. And that is the mechanism for T2 decay at the microscopic level. Okay, we're talking about microscopic spin level. Okay, spin level. So this effect is not actually a strong function of B0. It has nothing to do with B0. But it does actually have it is a function of the type of tissue that we're talking about. If your tissue is solid, so the spins are not moving, cannot move pretty much in space, so they're pretty locked to their position, then it's a very strong effect, because this one will be majorly affected by this, and this one will be also affected, and then the contribution of all those spins will, they lose coherence very quickly. However, if there is mobility and this spin is allowed to move, and this one is allowed to move, and this one is allowed to move, and this one is allowed to move, then yes, they all will see different fields, but on average, they will see a similar field. Okay, because they'll see all those fluctuations, but all those fluctuations are similar to everyone. So on average, you get kind of like, this coherency is being kept. And so in liquids, you'll see very slow decay of T2, whereas in solids, you can see a very fast decay. Okay, so it's very hard to actually image solid tissue compared to liquid tissue. And in fact, people that did NMR for a very long time realized that NMR in liquid state is relatively easy. You can actually have a very slow decay there. But NMR of solid state, oh my God, that was like super hard till people figure out that you can actually do stuff to the magnetization to make that liquid, make that solid appear as liquid somehow by rotating it very, very fast around a particular angle to eliminate some of those dipolar field effects. And I'll mention this briefly, but some of that effect actually we see in vivo as well. Okay, so let's try to describe this dynamic. First of all, when I look at the MXY component, really it is a vector, right? Like my magnetization vector is really MX, MY, and MZ. These are three components. But if you remember, only the transverse component is the component that contributes to MRI signal. We only pick up the signal from the transverse component. So it's the MX and MY direction. So what often people do in order to represent these two, like this vector MX, MY, to just represent this vector, You can also use just a complex number. Okay, it's just a very convenient way of describing the same thing. So often we use the mxy component and describe it as mx plus I my, where I is the square root of -1. And that's just a very easy way to describe this pretty much vector. Okay, it's just from convenience. And so in this case, we would have that the change in the mxy component with respect to time is equal to -1 over t2 mxy. Okay, so there is some loss mechanism that can be described using this linear dynamic equation. And what is the solution for this equation? Whenever you see something like this,
Exponential
yeah, it's exponential what?
decay.
That's right. And what if this was positive?
Then it'd be growth.
That would be amazing. You know why? Because we'll have infinite SNR. Because the SNR will just grow and grow and grow. We just have to wait, and then it just grows and grows and grows infinitely. So this would have been great. Unfortunately, not physical. So it doesn't work. So it is negative. Hence, everything is nice and stable and things just decay. Okay. All right. So the solution for this pretty much is mxy of t equals e minus t over t2 of mxy at time 0. Okay. That's pretty much the dynamic. And it kind of looks like this this decay. And this is a huge source of image contrast because this T2 here, this parameter T2, which parameter decay, sometimes actually it's called also R2. R2 is the inverse of, so R2 equals 1 over T2. Okay. So sometimes people refer to, this coefficient 1 over T2 as like R2, or they'll refer to as T2. So it depends. The units of T2 are in seconds, I guess. Okay, that's the units of T2. They're seconds. And this is pretty much the decay coefficient. And it's a major source of contrast because this T2 parameter differs for different tissues. As I said, if something looks more like a solid, it will decay, like the decay is faster. Then if something looks more like a liquid, then the decay is slower. So T2 would be longer for liquids, then it would be much shorter for solids. Okay, so gray matter, white matter, muscle, blood, cerebral spinal fluid, they all have a slightly different T2 parameter. Anywhere between something that's very close to 0 to about 3 seconds. Okay, 3 seconds or so for hydrogen. Okay. By the way, carbon-13 can have actually a T2 of about 45 seconds. Okay, so carbon-13. And this is what allows us to do some of the carbon-13 imaging in vivo. Okay, so here's an example, brain at 1.5 Tesla. Although it's not a big, T2 doesn't really change much with the field. White matter has a T2 of about 92 millisecond and a density of about 0.65, okay, with respect to just water, in terms of its amount of protons in that tissue. Whereas gray matter has a T2 of about 100 millisecond and then a density of 0.75. Okay, so it's a little bit more dense. Okay, so if we apply, let's say, a 90-degree pulse and move all the magnetization into the transverse plane, at this time point, our magnetization that comes from the white matter, right, is going to be, that large. It's going to be around 0.65, right? Because all the magnetization moved from being up into the transverse plane. And now in the transverse plane, we have a magnetization vector of about 0.65 in terms of intensity because this is the magnetization of white matter. whereas the gray matter will have about 0.75. Okay, so we'll have a higher because of its density. But then what you'll see is that the white matter decays at a slightly faster rate than the gray matter. So over time, this will actually decay faster than this curve. And so if we excite and then wait, let's say we wait for, I don't know, 100 milliseconds or so, then after that time, the distance or the contrast between gray and white matter will increase more than it was in the beginning. Okay, in the beginning is about 0.1, right? And here it will be much more significant. And so the way to get T2 contrast is to excite, wait. After we waited till the contrast is increased, then here we start encoding the information by applying gradients and doing all this stuff in order to and collect data. Okay, so all this time from, let's say, here to here, it's kind of like dead time that we're waiting for the contrast to evolve. And once we get to this time point, we're gonna make an image. And then we'll wait till the magnetization recovers, and then we repeat this again and acquire another set of data in K-space, and then do that again and again and again. Okay, so that's the idea. And this is just an example of an image that is T2 weighted. And you'll see that gray matter is brighter or lighter than white matter because of this effect. Okay, so this is gray matter. You see that it's bright, where white matter is much darker. And CSF, which is pretty much almost pure water, is extremely bright because that is even slower to decay, right? That has actually a T2 of about 3 seconds or so. Whereas gray matter is about, we said it was, what did we say it was? 92 or something like that? Yeah. So CSF would be extremely bright, then gray matter, and then white matter much darker. All right. So this is what we call T2 contrast. Now, I did mention something about this dipole-dipole thing, and that dipole-dipole thing affects solids significantly. And so if you actually look at tendons, tendons are pretty much semi-solids, right? Like they're flexible, but you know the spins in tendons are really bound to a very, very constraining structure. Okay, so what happens then? There's a nice tendon here, but then yeah, actually this is a better diagram. So here this is a very nice tendon over here that you can see. And normally we can't see tendons in MRI. They're just, you know, the signal decays so fast as impossible to see. But then here in this image, there's this super bright spot over here. You see this bright spot? This is actually a tendon. And what happens here is that this particular part of the tendon is also correspond to this point over here, is about 55 degrees. So here the tendon is oriented about 55 degrees with respect to the main field. This is where the main field points. And this tendon is actually oriented at 55 degrees. And then what happens at 55 degrees, the dipole field is actually 0. So if you have some spin oriented, so this is where the field is 0. So if you have all those spins kind of oriented along exactly the same direction, you know, where they actually don't affect each other, then the dipole field cancels, and the T2 of that tendon becomes really, really long, and though it becomes bright. But that's only when it's oriented at 55 degrees. When it's not, then the dipole field is significantly high, and then you get pretty much a dead signal. This is called a magic angle effect because 55 degrees is the magic angle of a dipole field. So at 55 degrees, you know, that's where the field is 0, which I think it's like it's this direction, something like that. And so that effect cancels. what other people doing when they're doing NMR experiments, they will take a tube where you have a solid, they'll orient it at 55 degrees, and then they'll spin that tube inside the magnet, and that would create a similar effect as what I've showed you here, and that way you can actually lengthen the T2 of solids significantly and have their signal last for a longer time. And this is called magic angle spinning, and it's used in MRI and NMR. Of course, we don't do that in MRI because you can't spin like really a sample in MRI, but in NMR, we have these small tubes. You can actually do that. Okay, any questions before we move to T1? By the way, some of the things, like for example, this effect over here, right, that I showed you. You know, you see this bright spot showing up, right? And that is effectively, I mean, it's a result of physics. It's physics that we don't model normally using, let's say, our block equation that we're going to derive, or, you know, this is really a quantum mechanical phenomena, right? Like you have to account all the spin relaxation stuff. So you get this brightening, and we call it an artifact, a magic angle artifact. It's really described by physics. It just is not described well by classical physics. And you'll see that in many cases, whenever you have a phenomena that cannot be described by the classical description of MR, we just call it an artifact. But of course, it can be described in other ways. So there are models for it. But you'll see in many cases that, you know, even if we don't model this, we can just call it an artifact and say, oh, this is an enhancing. And you just get a lengthening of the of T2. If you really want to dig more deeply into this, then you have to go through some mechanical, quantum mechanic, you know, interpretation, and then derive that in order to be able to see it. Okay, so this happens, for example, when we do chemical shift. Like where this chemical shift comes from? Well, it is something that related to all those shielding of the spins, but it's, you know, it results in an artifact, which, you know, image would kind of shift with respect to where it actually is supposed to be. So we just call it an artifact. So whenever we have deviation from this model, then we call it an artifact. All right. So what about T1 recovery? So we dealt with the transverse magnetization, but in fact, remember when we did the toilet analogy, we also had the situation where we had the tank of the toilet, and the tank of the toilet started filling up with water so we can excite it again. And so this is corresponding to the longitudinal component. And we also have this longitudinal relaxation. And this longitudinal relaxation, its source actually comes from not spin-spin dynamic, but actually spin-lattice interaction. So it's interaction between the spins and the molecular structure. Okay, so it's part of that. Basically, it's the thermal bouncing of these molecules where the spins are on that causes some losses effect in the precession that leads to that leads to the fact that those spins are going to align with the field. So it's a slow process. You know, it takes up to a second or so in order to be to happen. And that has to do with the interaction of the spins with the molecules that they're on. It actually has a very strong dependence on B0, okay? Because all this tumbling you know, it really, all this tumbling that you have is the growth of this magnetization depends really on the energy level between spin up and spin down that we talked before. And remember that this energy level really depends on B0. So if you have a stronger B0, the energy level between spin up and spin down is larger. So you need more energy, right? You need more energy to flip from one place to another. So what happens is that, you know, it doesn't happen as often. And so what you'll get is that as B0 increases, T1 becomes longer and longer. It takes more time for this relaxation to happen because it's hard to kind of switch between these states because of all this tumbling. Now I'm going to do some hand waving over here, and you might get it or you might not get it, but I just want to kind of give you an idea of kind of what's going on. When you look at an ensemble of spins, like just, spins, you put them in a strong magnetic field. Let's say this is B0, and you have some spins. Spins have arbitrary orientation when they start off. When you put them in a magnetic field, they instantaneously start precessing. And so this spin over here will start then precessing this way. This spin over here will start precessing this way. This one over here will start precess this way, and this one will precess this way. And they might have as well just kept precessing, and because all of them are oriented in arbitrary direction, we wouldn't get any signal whatsoever, and we wouldn't get any magnetization. Because they're just locked to their position, and they're just precessing, but they're just in arbitrary positions. Now, the thing is that these spins actually belongs to molecules, and those molecules kind of tumble along and tumble along and tumble along, and those create small fluctuations in B0 with respect to these spins. And we're talking about fluctuations of about 10 to the minus 4 degrees. This is very, very small fluctuations. Okay, so B0 kind of like, you think of it, it's kind of like moves around a little bit. And because B0 moves along, what would happen to that magnetization? It will start, kind of like wander a little bit, and then keeps precessing, and then wander a little bit, and then precess, and wander a little bit, and kind of precess, and wander a little bit, and precess. But because there's always bias towards up, then there slowly, there's going to be kind of like a distribution of kind of like a little bit more up spins than are less. You can kind of think of it as kind of like gravity, where you have a bowl, and that bowl is filled with, let's say, very heavy beads and more light beads. And when you put them inside the ball, I mean, like they're all kind of mixed together, right? And like the light beads are at the bottom, the heavy beads are, like they're just mixed everywhere. But if I kind of shake a little bit, I shake that, that bowl a little bit, because of the gravitational field, there will be a tendency, because of all this tumbling, for the heavier beads to actually come down, and the lighter beads to kind of float up. And this is a similar phenomenon that happens here. Okay, again, from an energy consideration. So effectively, if I actually zoomed in onto spins, okay, if I zoomed in, this is what I would see. Always. Because of thermal fluctuation, it's just going to look like that. However, if I look at a huge ensemble of spins, then you're going to see that there's, there's just like more of them are pointing up, and hence I'm going to get some bias in the field, and then magnetization that is going to be created because of this accumulation of all the spins together. All right. Again, hand waving. If you're interested in learning more about that, I would really recommend actually taking some quantum mechanics classes, and maybe in chemistry, taking a class on NMR, because that would be more, you'll see that more in depth. How do we describe this dynamic? Well, the magnetization will recover to equilibrium, right? Like the equilibrium M0. So the way we describe it is that the change in the MZ direction with respect to time equals to negative MZ over T1 minus M0 over T1. So the solution for that is MZ as a function of time. If you actually solve this, again, this is just a simple first order differential equation, which is solution is MZ of T equals M0 plus MZ of 0 minus M0, all that e to the minus T over T1. I mean, if you think about it, this is very similar to a capacitor type of, capacitor and resistor type of an equation, right? That, exponential kind of recovery to some voltage, right? So it's very similar dynamic if you've seen this before. Okay. Any questions? So how do we know that it does the right thing? Let's see. Let's put 0 over here. So at time 0, this would be M0, and let's say this was M0, so that's fine. So that will be give me my initial condition. And what happens at infinity? Okay. At infinity, this would equal to 1, right? Is that right? No. Oh, sorry. When this is 0, sorry, oh, hold on. When this is 0, then what I will have is I will have M0 plus mz of 0 minus m0 times 1, right, at time 0. And so what I will get is that this part will cancel with this one, and I will end up with the initial condition, which is fine. At infinity, now I'll take this to infinity. At infinity, the whole thing equals 0, and then I'll just end up with m0. Okay, so we'll recover all the way to m0, okay, with an exponential recovery. All right? Does that make sense? Everybody agrees with this formula as a solution for this? Any contestants? Okay. All right. So after we apply a 90-degree RF pulse, all our magnetization goes from pointing up, where all the magnetization was in MZ. After applying a 90-degree pulse, the magnetization MZ will become 0. Right? And you've seen that in the past, right? Like we had this graph here, and then we said, oh, we're going to apply a B1 field over here. Our magnetization is pointing over here, and then the magnetization is going to precess, and we'll end up over here. And this is a 90-degree pulse. Okay, so a 90-degree pulse will move all the magnetization from MZ into the MXY plane. Okay, so after that happens, then the MZ component as a function of time will start growing. It will start growing from M by this formula. So M0 minus M0 eta minus T over T1, which is effectively this. And effectively will exponentially recover back to M0. Okay. And that's again another major source of contrast, which I'm going to explain right now. So T1 contrast, brain at 1.5 Tesla. The gray matter has a T1 relaxation parameter of about 900 milliseconds. White matter has a relaxation parameter of about 800 milliseconds. So what we're going to do is we're going to excite 90 degrees. When we excite 90 degrees, all the magnetization goes to the MXY plane, right? So there's no MZ component. Okay. And then we just wait. We wait. What happens to the MXY component? Actually, you know what? Let me just draw up here what happens to MXY. Right? MXY, when MZ becomes 0, MXY becomes big, right? So I'm going to use purple for that. So MXY starts up here. And then MXY of gray and white matter will kind of decay, right? What's the rate of decay? Well, it's 92 milliseconds, right? So it's much faster than this, right? It's much faster. So the MXY component will decay very rapidly, while the MZ component still grows and grows and grows and grows and grows. Okay, so by this time point over here, there's really no MXY component anymore. There's just MZ component that's just growing and growing and growing. Okay, so what you can see is that the white matter will recover faster than the gray matter. And after a certain amount of time, where that space in magnetization between them is large enough, we can say, oh, now there is enough contrast between the white and gray matter that has developed, right? Remember, at the beginning, they started at 0. And after a while, the white matter now has a larger MZ component than the gray matter. At this time over here, at this time, I'm going to apply a 90-degree pulse again. What would happen when I apply a 90-degree pulse again? What will be the value of MZ, of MXY for the white matter?
Bigger than the gray matter.
Well, it's going to be somewhere here, right? This value, right? And the gray matter, I mean, remember, all the magnetization for MZ is being moved into MXY. So whatever MZ is, it becomes MXY, which we can actually then image, right? So then if this is the gray matter over here, then gray matter will be smaller. So now I will actually see something like that. So this would be the MXY component for the white matter. This one's for the gray matter. And then they'll start decaying, right? And so on and so forth. But once they actually show up in the MXY component, here is where we actually use the gradients to encode an image. Okay? Here is where we use the gradients to encode an image. The thing is, we can't observe the MZ directly. We can never observe it directly. So what we do is we, let's say, excite, let the MXY decay completely, right? So now MZ just rises and rises and rises. So now we have a difference in MZ, but we can't observe it directly. So once there is a big difference, then we apply an RF pulse to move the MZ into the MXY component. And then this is how we image the MZ indirectly, by moving it into the MXY. Does that make sense? So what you have to do in order to do T1 contrast is you have to excite once, wait, and then excite again to be able to see that difference. Okay.
Professor, I have a question. So with MXY, we're able to detect the MXY component with the same field that generates the RF pulse, or the same coil, right?
Yeah, for now, yeah, the same coil. So we switch this coil from transmit to receive. Yeah, there's a TR switch.
Right,
Yeah.
right. And then why can we not do the same thing with MZ and the coil that generates the B naught field?
That's interesting. Yeah, first of all,
Isn't
the
it
B naught,
I was just gonna say, isn't
Go ahead.
I thought the B naught field was kind of more like a big dipole in itself, or at least that's what I thought. Like we basically created like current. No, how do we create it then?
the B0 field is constant, right? Like it's just constant. It's uniform throughout the volume.
But how do we create it?
Right.
If we don't
you
use
have
like
you have a big superconducting magnet for that, right?
Okay.
And you put like a sample in that magnet. I mean, it doesn't have to be superconducting. It could be a permanent magnet, right? It could be just a permanent magnet that generates a constant field throughout a volume. Okay. The thing is that if you have to understand that, first of all, we can turn off the B0 field, right? So it's still it's still very large. And the MZ component, remember, is just DC, right? It's just that it doesn't oscillate MZ. MZ is just its magnetization that's pointing in the same direction as this huge field. We're talking about micro Tesla changes locally in a very small, in certain areas in your body, whereas you have a 3 Tesla big magnet on top of that. So it's just not possible to observe this because they're all on the same frequency. There's just DC, they're constant fields. The only field that's oscillating is the MXY component. The MXY component oscillates, and so there we can inductively couple to it and then differentiate it from the rest of the magnetization, because that's actually an RF field, so it's different, so we can distinguish. Does that make sense?
Yeah. So like we can detect, because I guess the MZ is technically changing, right? So we could detect the change in that direction, but it
No,
would
we
be the
can't.
sum over
No,
all
we
the.
can't. We can't detect it. No, we don't
Oh, we
see it.
can't.
Like, it
Okay,
happens, like it increases, but we can't detect that. We can only
I see.
detect it when we tip it back to the transverse plane.
Okay,
That's when we detect it.
got it.
What, Anita, you're trying to say something? You're muted, Anita.
This is a good picture of, on page 26 of the transmit receive coil. It's just physically located in that orientation.
Did you say 26?
26, figure 3-4.
Thank you.
Yeah, I mean, all you have to, if you remember, we said that we have, this magnetization vector and it's kind of precessing, right? If I put a loop here, if I put a loop in this orientation, then I mean this has field lines, right, that go through, and then some of these field lines will go through the loop. And then as this moves around and precesses, then you'll get different, change in flux through this loop. And that will create EMF with a loop, and that's how we can detect it. But there's just no way to see any effect on MZ. Okay, not this way. In fact, there's other ways that people actually do direct detection of MZ components using optical means, but that's very complicated, and it's not, you cannot do that in vivo, and not do that in an MRI kind of apparatus. It requires it's mostly detection of electron spin as opposed to nuclear spin. But I don't want to take too much of it. But inductive coupling, it only happens in the MXY component, and we can observe the MZ component indirectly by tipping it to the transverse plane and then observing it immediately. Okay, so this is how it's done. And this is pretty much what's called a T1 weighted image, where gray matter, okay, so here's the idea. Something that recovers faster, right? Its magnetization before the second RF pulse will be then larger. So whatever recovers fast will be brighter. Remember that white matter recovers faster, hence white matter in T1 weighted imaging is brighter than gray matter. And then the darkest thing possible is the CSF, because CSF is a very, very long T1, and it takes a very long time to recover, and hence it's usually very dark. Fat actually has a very short relaxation, so it has a very short T1 on the order of about 100 or 150 milliseconds. So it's much shorter, and hence subcutaneous fat is much brighter than the rest of the tissue. Okay, because it recovers the fastest.
When you have like contrast, like the when you actually get it in, like when you're getting like an MRI and they give you contrast, how does that affect this exactly?
Oh, that's something else. So when you put a contrast agent, so contrast agents, they either change the T2 of tissue, or they either change the T1 of tissue, or both. So for example, gadolinium contrast agents are often used because what they do is they shorten T1 significantly. If they shorten T1 significantly, then on T1 weighted images, wherever you have contrast, that tissue will look brighter because the T1 becomes shorter. If you put, how do you call this? USPI, like magnetic nanoparticles. So iron nanoparticles. If you put iron nanoparticles and you inject those into the body, then those have a tendency to create inhomogeneous field next to them, and that creates a very, very strong T2 effect. So it shortens the T2 significantly next to them. So often you'll see something as black, like the signal will decay much faster next to those. Okay, so these are the type of contrast that you'd see. So I want to talk about something called inversion recovery, which is something very interesting. So if you remember, at equilibrium state, our magnetization, so here I'm plotting MZ, MXY component, and this is RF, okay? And just before, in equilibrium state, my magnetization is some M0, some constant magnetization. What would that magnetization be after I apply a 180-degree RF pulse?
The other way? But negative?
If you just remember, let's say that was the B1 field, right? This is the magnetization, and then the magnetization precesses above the V1 field. So it precess, and achieve 90. When it reaches 90, then all the magnetization are in MXY, right? But who says we have to stop here? We can just continue on. We keep on the RF on, and then we achieve 180 degree. Where is all the magnetization pointing now?
Negative M naught.
Negative M naught in the, which
Z.
direction?
Negative.
MZ.
Z.
Yeah, so all the magnetization, we'll jump to here. Okay. And what would happen after that?
T1 relaxation.
T1 relaxation, right? So what would happen to the magnetization?
MZ will go back to the positive direction.
So it will basically relax to equilibrium, right? To M naught, right? So it would kind of go like exponentially, right? And relax to M naught. Yes?
Which
Okay.
direction does it go?
Well, it just grows, right? It'll just
Okay.
grow that way,
Okay.
up.
So it doesn't
Yeah,
like.
that's interesting, right? It
Right.
just grows up. No, it's not flip. It's not moving, right? It's not rotating. It's just relaxing. So it would actually, let me just show you. Yeah, no, that's a good point. So it will start here, and then this just grow across zero. At some point, there are going to be zero magnetization. And then after that, it will grow to be, positive. Yeah. It just grows along the MZ axis. So MY throughout this entire time will be zero. Till we reach this 90-degree pulse. What would happen with this 90-degree pulse?
MXY should become large.
MXY will take all the magnetization, whatever magnetization was here, will be transferred to MXY. Right? And then what would happen?
It decays.
T2 decay. That's right. And then what would happen to M naught over here?
It relaxes back.
T1 relaxation.
Yeah, it relaxes back. Yeah, the same way. Okay, so now we saw some dynamic going on here, right? Okay, So let's say this was gray matter. What about white matter? Actually, let's say this was white matter. What about gray matter? Gray matter, I don't have gray. Let's call it green matter. Okay, green matter in the brain. Let's say green matter in the brain as let's say it has a little bit of less M0. Okay, what happens after 180?
Negative Z.
It will flip, right? Yeah, right, negative Z. So it'll start here. And then let's say its T1 is longer. So it'll take more time to recover. Okay. What would happen at this point?
It would all go to MXY, but it would be less than the
Yeah.
white matter.
Yeah, that's right. And then I don't know, maybe something like that even. And then over here it will again grow, right? Okay. All right. Well, then here's a really cool way to create a big difference between gray and white matter is that I first perform an inversion, and then I let it recover, and then I perform a 90-degree. And then at this point, if I make an image of this, then I would see a big difference between gray and white matter. Okay, which is based on T1, right? It's based on T1. However, I can also do something else. Let's say I have water, like liquid, right? And liquid have a very long T1 recovery. So let's put liquid, let's say, pick a color, let's say put red. And let's say liquid is actually, it's pretty strong magnetization is over here. So this is liquid. What happens after 180? Ends up here, right? Okay. And then it recovers, and then it reaches this point. And for some reason, the timing of this 90-degree pulse is exactly when the fluid component crosses 0. What would be the MXY component of fluid?
Zero.
Yes, 0. That's right. It will be 0. Absolutely. And then after that, from here, it will also recover, right? So on and so forth, right? Okay. So now we've waited, let's say, so first of all, there's no signal now from any fluid whatsoever. And then I'm going to wait a long time. When I wait a long time, now the dominant source of contrast is actually T2. And I can actually make an image at this point. If I make an image at this point, I'm dominated by the T2 parameter. But what I've actually gained for this inversion is that I was able to null completely the signal from fluid that has a very long T1, but then still be able to get a T2 weighting from gray and white matter. Because if I wanted to do a T2 weighting just from, without doing all this trick, what would be the signal from fluid?
Should be the highest.
The highest, right? And so it can obscure a lot of tissue that maybe I might be interested in. And so this is called fluid attenuated inversion recovery sequence, where you prescribe the right timing such that you apply the second 90 exactly the 0 crossings of the fluid. And then you wait for T2, and then you got yourself fluid attenuated T2 weighted images. And this is the difference between T2 weighted, and this is fluid attenuated inversion recovery, T2 weighted. And you notice here, look, white matter is dark. Gray matter is brighter. Here, white matter is dark. Gray matter is brighter. It's still T2. However, the fluid, all this fluid, cerebrospinal fluid that was throughout the entire brain now is gone. Nulled. Isn't that freaking amazing? Look what we've done. Like, you know, fluid bothers me. Kill it. I'm going to kill it with RF pulses and timing. Right? Look at that. How different this image now looks from here. And you know what? What happens very often is that you might have edema due to stroke in the brain. And edema usually is a little bit lengthening of the T2. So it will show brighter on T2. I'll show you images after that of edema. But basically, what would happen is that in this area, it will be a little bit more white. But, you know, while this white that I plotted here is very bright, but think of it, it's just going to be buried in the fluid. Like you won't be able to actually see it very well. But now, after this is gone, well, now this brightness is going to show up so nicely, you're going to see this edema very easily. Okay, this is super powerful. Super powerful. In the same way, we can also remove fat. Fat has a very short T1, right? So what we could have done, oh, hold on.
I have a question.
Yeah.
So edema also contains water, right? It's fluid filled.
Yes.
So when you're doing the fluid attenuation, why isn't the fluid in the edema attenuated?
Because edema is more like 1200 milliseconds as opposed to 3 seconds.
Okay.
2 seconds. Yeah.
It's constrained more than CSF is.
Yeah, it's still constrained. It's not as, I mean, it's still brighter. There's more intercellular fluid because of edema, but it's not like it's free fluid.
Okay.
So it's still going to show bright on the T2, but it's not going to be nulled.
Okay.
And then I can also null fat because, like, let's say if I have fat tissue, you know, fat tissue will recover really quickly, like somewhere around here. And if I applied then the 90 over here, then fat would die. So this is called this is called FLIR, fluid attenuation inversion recovery, and STIR is saturation inversion recovery. It's meant for fat. Okay, so lipid saturation. So there's all sorts of tricks that people do, and sometimes you can apply, you know, at 180, wait a little bit, do another 180, wait a little bit, do another 180, and then you can null maybe 2 or 3 tissues with different values. Right, so you can really manipulate contrast by applying all sorts of 180s. There's a sequence called MP2 rage, which nulls the white matter and nulls also a fluid, and then you're just left with gray matter. Okay, so that's another very important sequence that people use, and that uses 2 inversions. So this is the whole relaxation. So our relaxation basically both transverse and recovery. So it kind of traces this type of a path. Okay, if T1 and T2 are the same, when T1 and T2 are the same, then effectively you trace kind of a I think a straight line if I'm not mistaken. But normally T2 is shorter than T1, and so you start getting these convex curves like that. Okay. All right, so if we combine these all together, the change in magnetization with respect to time is minus gamma B cross M, that's precession. Then I've got myself transverse decay. And then I got myself longitudinal recovery. This is really the linear dynamic, and this is called the Bloch equation. It's phenomenological, basically just fits observation. And it was first described by Bloch, Felix Bloch. Now, sometimes it fails. Sometimes there are issues like J coupling, magnetization transfer, all that stuff that cannot describe this. And then we call this an artifact. Okay, that's really what happens. All right, so with that, I think I'm perfectly done with this set of slides and lecture. Hopefully now you have a better idea of what is really the dynamic. So we're talking about when we apply fields, like any B fields, either B1, B0, or gradient fields, those cause rotations and precessions. And then once you have magnetization in the transverse plane, it immediately starts decaying with parameter T2. And then if you have magnetization that's not at equilibrium, it immediately starts relaxing with parameter T1 in the Z direction. Okay, this is really all the dynamic that will govern, classical MRI. And that's what we'll use in class in order to perform selective excitation and signal acquisition. And so next time, what we're going to do is we're going to solve the block equation for the reception part and be able to basically derive k-space, like how spatial frequencies come from solving the block equation. And then that will lead us to how we sample in the frequency domain and like how should we choose those samples and so on and so forth. And then after we're done with that, we're going to go back and talk about RF selective excitation again. Okay. Pretty awesome, right? So hopefully now you have a better pictures of what's going on. I hope you will enjoy the homework. The homework, I don't think it's too challenging. We'd have one MATLAB exercise that would require you to, or a Python exercise, which would require you to design what we call a time optimal gradient waveform. So basically gradients are not perfect. You cannot just turn them on and off. You have to actually ramp them up and to reach a certain value and then ramp them down. So one of the tasks that we're giving you is to design a certain gradient area given some constraints on the gradient system. And we'll use this when we actually go and simulate a whole MRI acquisition. When we do that, we're going to run a block simulator. And we're going to simulate an MRI acquisition. We're going to use this in order to do that. Okay, so hopefully you'll get it right. And if you don't, we'll give you a solution so that it doesn't mess you up in the next homework. We're going to rely on that. Have a nice weekend, folks. Stay safe. 2 masks. Definitely N95s if you go to shopping or public transportation or something like that. Wear an N95 mask and a cloth mask on top of it. And if you go public transportation, don't be ashamed, put a face shield. That will give you pretty reasonable protection. Eli Ablanovich, who's one of our senior faculty, maybe he's going to be a Nobel Prize laureate in the future. Who knows? He's not afraid to go to all those stores while wearing swimming goggles and like an N95 mask and also a face shield on top of that because he doesn't want to die because of the Nobel Prize. Maybe, I don't know. Don't quote me on that. Eli, I'm rooting for you. All right. See you, folks.